So here we have example 1. Test grades are normally distributed with a mean of 78 and a standard deviation of 12. We just know that this test grade that's given to college students has this mean historically and standard deviation. And we take many samples of 49 college students who have taken this test. Okay? We want to find the mean for the sampling distribution of sample means. So again, the mean of means, mu sub x bar, and I don't know how to do a subscript on here, so so that's the mean of the sampling distribution is mu sub x bar is always just going to be equal to the population mean. So the mean of the sampling distribution of sample means is 78 because I'm taking many samples of it. And if you think about it, and we'll get to this in a minute, the more people I have taking this test, if I take all of their scores together and average it, shouldn't that get closer and closer to 78? Now, I might take a sample of people who happen to do really well on this test, and I might get a sample mean that's more than 78. But then I'm going to take another sample mean, and that sample mean might be less than 78. And I might take a sample where the sample mean is exactly 78. And when I average together the mean that was slightly more, the group that had a mean that was slightly more than 78, and the group that had a mean that was slightly less than 78, and the group that had a mean that was exactly 78, and I average those eventually, and I have enough groups, many samples, I'm going to end up with the same mean as the population mean. Now the standard error, and this is sigma sub x bar. Actually, we can just call this standard error. That's going to be equal to the population standard deviation, which is 12, divided by the square root of the sample size. So I'm taking a bunch of samples of 49 students. And so that's going to come out to 1.714. The square root of 49 is 7. 12 divided by 7 is about 1.7. Okay? Notice that the standard error, the standard deviation of all the sample means, is much smaller than the actual standard deviation of the population. That's again because I'm taking a whole group of people who have taken this test and I'm averaging their scores. There's going to be some people that did poorly, there's going to be some people that did well, and there's going to be some people in the middle. But when I average their scores, it's going to be somewhat close to 78. And if I do that many times and then I average all of those sample means, not only am I going to be really close to 78, but the distance between the other means is also going to be much smaller than an individual person that I pull out of this population to see what their test score is. So now let's talk about the shape of the sampling distribution. So the shape here is we're taking a sample size, n is greater than 30, and the original test grades are normally distributed. So let's say that in this problem, the samples were only of size 20. Now my standard error would be different. My mean would be the same. My standard error would be different because then I'd be multiplying or dividing by the square root of 20, which would give me a bigger standard error. But even though n would be less than 30, because my original population was normally distributed, I know that my sampling distribution will also be normally distributed, even when n is less than 30. Okay? So now, let's find the probability that one student would have a grade above 90. So this is review of stuff that we've already been doing. We know x, we know mu, we know sigma. That's not sigma. We know sigma. go. We know sigma. So in this case, above 90, mu is 78. Sigma is 12. So to find the probability that one student got above a 90 is the same thing as 1 minus the probability that a student got less than a 90. And the way that we find the probability that somebody got less than a score is with our norm dist function, norm.dist. So that's going to be, I have a 1 minus here. Let's not forget the 1 minus. 1 minus. And then norm.dist of x, comma, mu, comma, sigma, comma, true. And so what that gives us is a 15.87% chance. So the probability that a single student selected randomly would get above a 90 is 15.87%. And that's the sentence I'm going to write for my final answer. Okay, so the probability, if I randomly select a student from the population, what's the probability that that student got above a 90 on this test? It's 15.87%, which isn't high, but it's not like crazy. Okay, 15%. That's doable, right? That's something we would expect to see. One out of 6 times, 7 times, 1 out of 7 times sounds about right. Okay, 1 out of 6 or 7 times a student's getting above a 90. Okay, so now I'm going to take 49 students out of the population. Each one of them has taken this test. I'm going to ask them what they got on the test, and then I'm going to take all their scores and I'm going to average them. What's the probability that the entire sample has a mean that is higher than 90? What is the probability that I happen to pick 49 students that all got an average of 90 on that? So that means if the average was a 78 on this assessment, we know that 50% of students got below a 78 and 50% of students got above a 78. If I am getting a sample of 49 students that has a mean that's above 90, that means that I randomly selected students that are all basically from 80 to 100. If 80 were the low score and 100 was the high score, those would average to a 90. And if we're saying above a 90, that means probably more like 81 to 100 are the score ranges. So I've only randomly picked 49 students that have gotten those scores. What's the probability that I do that? Well, X is still 90, okay? The mean is still 78, but now my standard error, sigma, my standard error, and why am I using standard error here instead of sigma? Because now I have a sample of 49 students instead of just one individual student. And so we already found that value. It's right here. It's 1.7143. Okay. Now let's find the probability that this student, or that this group of 49 students has a mean above 90. So the probability that X is above 90 is still 1 minus the probability that X is less than 90, which is found using my norm.dist function. The mean is, or the value is 90, the mean is still 78, but now my standard deviation is much smaller because it's a standard error. true. Now when I do this, I forgot my 1 minus. I get 1.28 times 10 to the negative 12. That is 0.000000000127. That's a lot of zeros. This is essentially zero. This is approximately 0. And so what changed? Why is our answer for part D so much bigger than our answer for part E? And that's what we've been talking about. Getting a single student, picking a single student at random, it's not that hard to believe that that student, especially if they happen to do well in general, got above a 90. But if I gather 49 students and average all of their scores, for their score to be that high above the mean, for their average score, all of these students, I have a couple students that maybe got a 20. I have a couple that got, or I have a student that got a 20. I have a couple students that got a 50. I have a couple students that got 90s. I have a couple students that got 70s and 80s. I have 49 different students, and I'm averaging their score. Shouldn't that average be really close to 78, even if it's a random sample? It'd be hard to believe that I'd take a random sample of 49 students that all happen to do above the mean on this assessment. So again, there are more students to draw from in example E. So it is less likely that they will deviate, that their averages would deviate from the mean. But what can we do? How can we make it so that in part D or part E, we have a greater mean or a greater probability than in part D? Well, what we can do is if 78 is in the interval that we're looking for, if I found the probability that X was less than 90, then my answer for part E would be really close to 1. Because remember, I did 1 minus the probability that X was less than 90. If we look at just norm.dist without the 1 minus, it tells me that it's 1. It rounds it to 1. It's not exactly 1, but it's really close to 1. So when I do 1 minus that number and I get something really close to 0, it's not surprising. So any interval, it doesn't have to be less than 90, but any interval that would include 78 is one where part E would give me a higher probability. If I take 49 students and give them a test, and then I average all their scores, that score is going to be really close to 78. Because historically, we know that's what people get on this test as an average. There are some people that do really well. There are some people that don't do so well. When we average them together, we're getting 78. It is very unlikely that we're going to sample 20, 30, 40, 50, 100 students and not have a mean close to 78. So as long as you include it's called the true mean of the population in the interval and the sampling distribution mean, or the sample mean, the the sample mean will have a higher probability than the individual mean.